Hello students, welcome to Talk on Civil Engineering. Let us see how we'll calculate the stresses in a pre-stressed concrete member if the tendon is provided with some eccentricity. Okay, so here you have one example. So here we have a beam and a tendon is provided with some eccentricity E from the neutral axis. Okay, so here you will be having pre-stressing force like this. So the pre-stressing force is provided at the eccentricity E from the neutral axis, that is just below the neutral axis. Okay, so at this case, for any pre-stress member, we will be having stresses. One, that is the direct stress due to pre-stressing force, and two, the stress due to eccentricity of pre-stressing force. And we'll have the self weight of the member, and some external loads are also acting on the member. So we'll have stresses due to self weight plus the live load. I mean the external load. Okay, so these three are the common, or the four maybe. If you take this live load separately, it will be four. So these four loads will be commonly acting on the pre-stressing concrete member. Okay, so for this eccentric member, for this the tendon is provided with some eccentricity. So at that case, so the direct stress will be this direct stress always will be positive. So that is P by A. So this is area of concrete. So P is the pre-stressing force divided by the area of concrete. Okay, so you'll get the direct stress. Okay, and remember this will be positive. Always this stress will be positive. Okay, so in case since this is a straight tendon, so this is a straight tendon with some eccentricity E having the uniform eccentricity. So for this case, if you take stresses at the support or at the center, the stresses will be same. Okay, so at the support, at the center, the stresses will be same. Okay, so therefore there won't be much changes in the formula. Okay, so coming to the stresses due to the eccentricity. So due to eccentricity, we will be having plus or minus PE by Z. Z is the section modulus. Okay, so section modulus of this rectangle, maybe the rectangular section or I section, whatever the section. So for that section, that the section modulus. P is the moment due to the pre-stressing force. Okay, so due to we are calculating the second one is due to the eccentricity of pre-stressing force, right? So the pre-stressing force is located with some distance. So we need to take the moment at the distance. So the moment divided by section modulus will get the stress. Okay, and plus or minus will represents so where the stress you are calculating. Okay, so for this case, if you take the for the same case, so here this is my beam. Let it be the central axis, the neutral axis, and my tendon is provided below the neutral axis, right? So because of this force, I will get the moment. So something like this. Okay, so because of these moments, so my beam tends to have a hogging bend, something like this. Okay, so here this is tension. We all know this is tension, so it will be negative, and this will be compression, this will be positive. Okay, so on top of the neutral axis I'll get positive, negative. Below the neutral axis I will get the plus, compression. Okay, so if I want to calculate the stress at bottom, so I will consider plus here. If I want to calculate the stress at the top of neutral axis, so I will consider minus here. Okay, and coming to the third and fourth, both are similar. So that is stress due to self weight and live load. So for that, again, so let it be let me change these symbols to minus or plus, because on top I'm getting minus and bottom I'm getting plus. So let it be minus and plus. And for stress due to self weight and live load, I will get plus and minus. Plus and minus, moment due to the dead load divided by section modulus. So this is due to self weight. This is due to self weight. Okay, and plus or minus moment due to live load divided by section modulus. This is due to live load. Okay, so here I'm getting plus or minus. That means plus on the top of the neutral axis, minus on the below the neutral axis. So here, so this is purely due to the loads. So this is not due to the preceding force. Okay, so if you consider, so here if you consider the external loads, due to these external loads, we know the beam tends to bend something like this, like a sagging bending. You will have a sagging bend. Okay, so something like this. Okay, so that means above the neutral axis, you will have compression. So this will be plus because it is compression. Below the neutral axis, you will have tension. So this will be negative. So that's the reason I have given plus or minus. Okay, plus on, I will take plus if I want to calculate stress above the neutral axis. I will take minus if I want to calculate the stress below the neutral axis. Okay, so this is how I'm going to calculate the stresses. The stresses if the tendon is straight and having some eccentricity with the neutral axis. Okay, in case if the tendon is not straight but it is parabolic, if it is parabolic, so something like this. Let me draw here. So this is my neutral axis, and my tendon here, my tendon is, so something like this. So it is a parabolic tendon. Okay, so this is my tendon, and it is having a parabolic profile. So it is having a parabolic profile. Okay, so if you consider this one, so it is having eccentricity E at the center, and it is having zero eccentricity at the support. So E is equal to 0 at the supports. Okay, so at that case, so the stresses will be differ from the support to the center. Okay, so that means, so for the same formulas, here E will be equal to 0 at the support. That's it. That means you don't have the stress due to eccentricity at the support because the eccentricity is 0. So let me write the formulas. So the first one, due to direct stress, again the beam bends due to the pre-stressing force, the beam bends like this only. So it will have the hogging bending itself. So that means due to pre-stressing force, you will get negative on top, positive on bottom. Okay, so due to direct stress, it will be positive always. At the support and at the center, you will have the same formula. Okay, so at the support and center, so it will be plus P by area of concrete. Okay, so due to eccentricity at support, it will be PE divided by Z. But here E is my eccentricity at support is 0, so therefore it will be 0. So you won't have the stress due to eccentricity at support. But at center, I'm having eccentricity E here, so it will be PE into Z. And my sign convention is above the neutral axis it is minus, below the neutral axis it is plus, because it is a hogging moment. So because it is a hogging moment, so it will be minus and plus. And coming to third one, that is due to self weight and live load. So at support and at the center, the formula will be same. Okay, at support and at center, so it will be plus or minus. At above the neutral axis, it is positive again. At the below the neutral axis, it will be negative because it is a sagging bending, right? So it will be MD divided by Z. For live load, it is plus or minus moment due to live load Z. Okay, so this is how we are going to calculate if you have a tendon profile, something like this. In case you will have another case also, that is, so see here, so here my tendon is having eccentricity at the center, and even at the support also I'm having eccentricity of E2. Okay, so at that case, I will get the different stresses at the support and at the center. Okay, so whenever you are calculating the stress due to eccentricity at the support, we need to take E2, and stress due to eccentricity at the center, we will be taking the E1. And if you observe here, so if this pre-stressing member is not loaded, that means if there is no external load is not provided, so in that case you will have the stress due to pre-stressing force and the stress due to the eccentricity of pre-stressing and the self weight. Okay, so you need to have an idea of where the stress you are calculating, at what stage that you are calculating the stress. Okay, usually there are three loading stages are there, or three analysis conditions. Three stages. This is stress due to. Okay, so the first one, that is initial stage or the initial condition. Okay, so at this initial condition, you will have the stress only due to pre-stressing force. Due to pre-stressing force, that means the pre-stress, the direct stress, as well as the stress due to eccentricity. Okay, and the second stage is the transfer stage. That means the pre-stress is transferred to the member. That is called the transfer stage. So at this stage, you will have the stress due to the pre-stressing force plus the dead load. I mean the self weight of the member. And the third stage is a working or the service stage condition. Okay, so at this stage, you will have the stress due to pre-stressing force plus the dead load and the live load. Okay, so you need to know what are the stages, or at what stage you are calculating the stress in the member.
Let us see how we can draw the stress distribution diagram for the tendon which is eccentrically provided, maybe a straight tendon or a parabolic tendon. So let us see how we'll draw the stress distribution diagram. Okay, so firstly, let us draw a rectangle which represents the rectangular beam. Okay, so I am having a tendon below the neutral axis. Okay, so for this, let us draw a reference line at top and the bottom. Okay, and the center as well. Draw the center line as well. Right. So first you will be having the direct stress. Okay, and as we discussed, the direct stress will be always positive. Okay, P by area of concrete, right? So it will be positive. Okay, so this is positive, and let us write the formula also plus P by A. Okay, and this is the direct stress. Okay, now we got the stress due to the eccentricity of the tendon, and it will be negative above the neutral axis. See here, so it will be negative above the neutral axis and positive below the neutral axis, right? So draw a straight line. Okay, so here I'm representing negative in left side and positive on right side. That is up to you. So here I'm representing negative on left side and positive on right side. And draw an inclined line joining these two corners and changing the sign at the center. Okay, so this is negative and this is positive. And formula we know. So it is here it is plus PE by Z. Here it is minus PE by Z, and this is plus P by area of concrete. Okay, so this is due to eccentricity of the tendon. And these two stresses are due to the pre-stressing force. Okay, now let us calculate this. Let us draw the stress distribution diagram for stress due to the self weight. Again, draw a straight line. Okay, so here due to the self weight and the live load, the stress will be positive above the neutral axis and negative below the neutral axis, right? So positive stress so above the neutral axis it is positive, below the neutral axis it is negative. And write the formula. So it is negative moment due to the dead load divided by z and plus moment due to the dead load plus moment due to the dead load divided by z. Okay, and now we have the stress due to the external load. Again, due to the external load also, above the neutral axis it will be positive, below the neutral axis it will be negative, plus or minus, right? So let us write the formula. So it will be minus moment due to the live load divided by z plus moment due to the live load divided by z. Okay, so this is stress due to dead load. This is stress due to live load. Okay, now we'll get, if you add the top stresses and bottom stresses, you will get the resultant stress. Okay, so for that, draw a straight line. So usually in pre-stressed concrete, mostly the at the end the resultant stresses will be in positive or else it will be zero. So you won't get any negative stresses. That is, you won't get any tensile stresses in pre-stressed concrete. That is the whole concept of the pre-stressed concrete structures, right? So it will be towards the right only. Okay. So this is the resultant stress. So this resultant stress is the summation of top and bottom. Okay. Yeah. So this is how we are going to draw the stress distribution diagram. Thank you all.